Newton's binomial theorem. Let's go ahead and break it down. Right up at the front, we have our a, so that's our first term here, a constant raised to the nth power, which is given. And then we have this sigma notation. Sigma notation is great for making concise formulas, but it can be kind of hard to see what it's saying. So let's take this sigma and start to expand it out. So we'll start with our a to the n first, and then we're going to take this expression here and put that in brackets as we expand it. Hopefully you've seen sigma notation. Our bottom number, r equals 0, that's the number we plug in first. So we're going to take 0, and we're going to plug it into here and here, this whole expression. So we're going to get n, choose 0, like that. And then we're going to get bx over a, all raised to the r power, where r is 0, like that. And this is the very first term of our summation notation, if we put it in expanded form. And then we repeat this process. So we take r is equal to 1, we get n, choose 1, and our expression here is bx over a raised now to r is equal to 1, and so we get 1. And maybe we can put up here, r equals 0, r equals 1, r equals 2. We'll just do the first, maybe 3, we'll do the first 3. So r is equal to 3. And so our next one, just like before, n choose 2 now, bx over a, oops, that should be over a, all raised to the second power, and then n choose 3, bx over a again, all to the third power, and then again, keep in mind, this summation goes up to infinity, so this is an infinite series of terms. Our next question is, well, what does it mean to have n choose 0? So down below here, we're going to try to break that down a little bit. Let's give ourselves a little space. And we'll kind of take a look at what it means to do n choose 0. That's getting into factorial. Oops, let's move that there. That's getting into factorial notation a little bit. So if we have n choose 0, another way to write that is n choose 0. We're using our n choose r formula. So n choose r has the formula n factorial over r factorial n minus r factorial, like that. And so here, this is going to be equal to n factorial, n is n, and our r is 0. So we're going to get 0 factorial, and then n minus 0 factorial, like that. And that simplifies to n factorial over 0 factorial is 1, n minus 0 is n factorial. We have n factorial on the top and bottom, which cancel, and that gives us just 1. And this term here is raised to the 0th power, so we can imagine that this whole first term is just going to be 1. We'll simplify down below. All right, let's try one more of these, maybe 2 more of these. What about n choose 1? What do we think n choose 1 would be equal to? Yeah, we're going to follow that same process. So here we do n choose 1. We're going to get n factorial over, again, our r is now 1, so 1 factorial, then n minus 1 factorial. And in our next step, we have to do a little bit more simplification here. We keep in mind that n factorial is n times the number that's 1 less than it. So if you have 7 factorial, that's going to be equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. So what's a number that's 1 smaller than n? N minus 1. And then we get n minus 2. And this is going to continue until it gets down to 1. On our bottom, we have 1 factorial, which is just 1, and then we have n minus 1 factorial, so that's n minus 1, and then a number that's 1 smaller than that is going to be n minus 2, and then again 1 smaller than that, and that continues again all the way down to 1. And so we can simplify this whole expression by canceling all of the like terms. So our n minus 1 minus 2 will cancel all the way down to 1 for those two. And that leaves us with a really simple result. This is just n. And then we can repeat this for n choose 2. This will be the last one we do. And we should be able to spot the pattern by now. So this one, again, we get n factorial. In our bottom, we get 2 factorial. And then we get n minus 2 factorial. We simplify that. Again, top is going to be n times n minus 1 times n minus 2, going all the way down. This is going to be 2 factorial. We'll just leave that as that. And then here, we're going to get n minus 2, n minus 1, and that goes on. Oops, that's not true. We're going in the wrong direction. That should be n minus 2, n minus 3, n minus 4. And that goes on down. And once again, if we simplify all that out, we cancel all the like factors, all of those will cancel, and we get, nope, make another mistake there. N minus 1 does not cancel. So we're going to get n minus 2 cancel, that cancels, that cancels. And that leaves us with n over 2 factorial, not a question mark. Let's try that again. 2 factorial. And then in the top we have n minus 1. And so you might notice a pattern starting to emerge. And the pattern, if we kind of highlight here, we get 1, and then n times n minus 1 over 2 factorial. And we can probably guess from this pattern what our n choose 3 will be. If you can't guess, you might have just an intuition that we're going to get one more term on top, and then down the bottom we're going to have 3 factorial. So this is kind of what our expansion is going to look like. So if we take all of that and we put it all together, we're going to get an expanded form of this formula. We get a plus b to the n power. Up here we have a to the n out front. And then inside the brackets, let's use brackets, keep it consistent. We're going to have our very first term, which is n choose 0. N choose 0 is 1. And this term, anything raised to the 0th power, is 1. So we get 1 as the first term. Our second term is here, n1. And we know that n choose 1 is going to be n. So we're going to get n here. And if we want, we can even put a 1 factorial down there. We kind of left it out from this step, but it's there. And that will make it seem a little bit easier, the pattern that we're going to see emerge. So we have n over 1 factorial, and then we're going to have bx over a, all raised to the 1 power. Maybe we can zoom out a little bit here so we can see everything together. Our next term is going to be our third term. So we have n choose 2. N choose 2 is this right here. So n times n minus 1 all over 2 factorial. And then again we have bx over a to the 2nd power. And we're starting to run out of space, so let's maybe shrink this down a little bit. Maybe put it on 2 lines. So we're saying a plus bn is equal to this. And we can say that our third term, which is this one here, actually that's our 4th term. Did we miss one? Let's see. So we have 1, that's 1. N choose 1 is this one here. That's correct. And then our square is that one. 1, 2, 3. Oh, I can't count. Okay, this is our 4th term. So our last and 4th term is going to be n times n minus 1. Let's zoom back in a little bit. And so we get n n minus 1, n minus 2, all over 3 factorial. And then again, we have bx over a to the third power. And so that's the first 4 terms of the expansion. If we needed more terms than that, you can see this pattern. So we notice that, again, for our denominators, we have 1 factorial, and 2 factorial, and then 3 factorial. So the next term would be 4 factorial. If we want to look really closely, this one here technically is 0 factorial. 0 factorial is 1, so 1 divided by 1 is 1, and we're not including it. And so this is the expanded version of Newton's binomial theorem. So this is Newton's binomial theorem here. Let's go ahead and, well, we'll leave the brackets there. Let's just copy that down. So this is the expanded version of this formula right here. Let's erase that and erase that as well. Now this expanded version is much more human-friendly. We can make sense of what's happening here, whereas this one, it takes a bit of interpretation. So we kind of have to take it from the really concise format and remember what the math means to get to here. The good news is that in IB Math, this expanded formula is available on the formula sheet, and that's the one that you'll be referring to as you work through questions and problems. And so the expanded version of that, we can go ahead and put in as well in the TAC format, and it looks like that. So here's our concise version, and this one is our expanded. All right, so that is Newton's binomial theorem